introduction, Helena, and great to see a lot of familiar faces and also to meet a lot of new faces as well. So look forward to connecting with everyone after. Just screen share. So as Helena mentioned, we're based in Silicon Valley in California. And I'll talk a little bit about our company, Current Laser Systems, and as well as our partner in automation, Owens Design. And similarly to some of my colleagues here, we are a laser system integrator. So we build full turnkey laser micromachining systems. And I'll focus a little bit more today on not just the laser optics and micromachining side, but also on automation, which is a critical part to high throughput manufacturing. So. Just very briefly, the types of tools we make standalone laser micromachining tools. So these are manual load tools where you can input a wafer, a sheet of material. We work with medical devices, variety of different materials for micromachining. We also build fully automated systems. There's often these standalone tools are then partnered with things like a wafer front-end module if you're working with wafers or solar cells. We also build fully custom automated robotic solutions as well to be used with these laser micromachining systems. And then we can also build fully 100% customized laser micromachining solutions for a variety of applications. It really depends on the application of what type of equipment would be best to support it. So, one of the wonderful things that we see here in the micromachining space is that it gets to serve a variety of different industries. Based here in the Bay Area of California, we see a lot of work with medical devices, particularly medical implants, semiconductor applications. Battery is a very hot area right now where we're seeing a lot of new materials, a lot of very challenging materials to process, and micromachining has a huge role to play in the battery and energy industry as well. For solar manufacturing, particularly scribing and dicing of solar cells, we're seeing a lot of micromachining applications there. And of course, consumer electronics, display, VR, AR, they all have manufacturing challenges that leverage micromachining today. So, the types of lasers, optics, processes we work with, kind of listed a long list of applications here. I'd say at Current Laser Systems, we primarily work with femtosecond lasers and picosecond lasers. So it's great to see a lot of conversation here today on those. But we still do a lot of work with nanosecond, fiber CW, and CO2, often as a complementary laser source to the ultra-fast lasers. And the types of processes we'll do involve many different types of processes, including ablation, cutting, dicing, drilling, etching, micromachining, welding as well, to just name a few of the core processes that we'll work with, and across a variety of different form factors. So one of the fun challenges we have in the automation space is working out how do we not only use the lasers, but how do we bring the materials and handle the materials in unison with the lasers and bring it all together. So something I'll talk about a little bit differently today, instead of diving deep into the types of applications and processes, a little bit more about the philosophy for how we approach this. And I think this is very complementary to the discussions that we've been having today on optics and lasers, is how do we go from, all right, I have this application, which maybe, we were just talking about glass cutting before and using different optics there. How do we go from these creative ideas to a solution that's ready for 24/7 industrial manufacturing? And one thing I'd like to share with you today is our phased approach that we highly recommend to use in the industry, because there's often a big gap between a quick test that's done in a laser lab or applications lab and having the solution ready. And we often like to break this into critical phases. Really sort of it's a program management approach where we look at the risks, we look at all the challenges that manufacturing would have. And this is a really critical step. We don't just look at the laser processing side of things. We also look at the manufacturing side of things as well. Things like, how are materials going to be fed in a manufacturing environment? Do we have tolerances to the materials, different thicknesses of materials as you go from batch to batch? All these really critical nuances in manufacturing that are really important to understand, and really recommend for those of us in the laser industry to work very collaboratively with automation. This will be a critical step to avoiding the infamous valley of death, where essentially, manufacturing lines sort of power up and you have this equipment running and the laser processes and systems just aren't meeting the specification if you don't consider things carefully. So we have a methodology for doing this at Turnley Systems and Owens Design, and this is really based off of a 40-year process that Owens Design has built, where they look holistically at the technology, manufacturing, and business needs of a specific application, and then we break it down into critical phases. And often we'll develop these laser processes. We'll try different optics, different lasers, different setups, fixturing, airflow. They all make a big difference. But a lot of the times we'll develop that in parallel with the automation, and they go really hand in hand. And a critical thing that we've learned in years of working together with Owens Design is not to develop process or laser technology in a bubble, and really to work collaboratively with your automation teams, understanding things like the upstream and downstream process needs is really critical. And this has led us to great success in deploying these solutions in large volume manufacturing. Just a little bit about our laser platforms that I mentioned. We're a custom laser machine builder, so we tailor these machines to the application. And here what we're trying to do is select the appropriate laser optics for the application, so to maximize the ROI from a commercial standpoint. And a lot of the work that we do in developing these phased development projects go into that tailored configuration in all of our machines. Here's an example of one of the machines. I think Dr. Reddy was asking about glass cutting. This was actually a machine that we had built that had glass cutting built into it. This was for a medical application, wafer scale. This was also doing via hole drilling and glass-to-glass welding, glass-to-metal welding, and some ablative processes as well. Really critical to these types of processes, we haven't really talked a lot today, are things like motion control. So motion control, precision motion, things like vision systems, sensors as well, because a lot of times we have to measure the part before we can process it with a laser. We've been talking about things like high numerical aperture optics and things like that. It's really critical you have your laser in focus and on the part. So bringing all of these technologies together into an integrated solution is really critical in manufacturing. Besides the laser and the laser process, often being able to feed materials into the laser machine is critical. And, understanding things like, am I able to process the material from one side? Am I allowed to flip the material over? Can I handle the material in certain ways? All of these constraints that we have in manufacturing really affect the process and the laser solution that's going to be applicable. So we provide these automated solutions for feeding materials into these laser machines as well. And then we can, of course, do things like the factory automation to communicate between our automation systems and the full factory. And besides just standard wafer loaders, we can also do fully custom automated solutions. And this was an example of a battery material processing that was done essentially and involved robotics, automated loading, unloading, laser cutting with femtosecond lasers, galvo scanners, coordinated stage motion. And then we had to post-process. So we have to clean the materials afterwards, remove the debris. Most of these ablative-based processes are going to create debris, and there needs to be ways to handle, mitigate, and post-process remove. So that's briefly about our companies, and nice to meet everyone here. And in terms of what can we do for you, what we can do for us, we're really looking for partners, whether these are customers and users, suppliers, who sort of align with this philosophy of approaching things systematically, methodically, and working through developing things to create turnkey manufacturing solutions. So, thank you.
Thank you very much, Mark. And the story of Turner Laser Systems is actually pretty cool. And we just wrote an article for Laser Focus Wall. It's going to be published in the next edition, in which you can find everything about this company. But Mark, and also Jose from LASEA, in previous discussions, we talked about the state-of-the-art on femtosecond laser-based surface structuring, hydrophobic solutions, antibacterial surfaces. What is the current state of the art on this? Are we ready to develop this for large surfaces? First, Mark.
Yeah, I mean, a lot of the challenges I've seen over there is the surfaces often aren't flat. So, having motion systems with multi-axis control, metrology is really critical in those types of applications. And so, I'd say the applications we've worked on, we've had to do, three-dimensional surfaces, even getting inside holes or grooves and channels in those cases. So, the motion control has to be one of the biggest challenges.